In section 2C, we're going to focus on the idea of bivariate data. So bivariate data, of course, is when you have two variables. We've talked about in the last two sections the idea of univariate data when we have a single variable. Of course, in a study, you can have many variables. You can have, if you give a 50-question survey, you can have 50 variables. So we focus in this class on having either one or two variables. So when you move from a single variable to two variables, essentially what you do is you move from a one-dimensional space to a two-dimensional space. It's like in algebra where you look at a single variable, you look at a real number line. When you move to two variables, you have that xy plane, which gives you your two dimension, your x dimension and your y dimension. So we do the same basic thing in statistics. When we have a single variable, we look at something like a bar graph. Really, the only axis that represents the variable is the x-axis. We look at the categories in a bar graph for that variable. In a histogram, it's the same idea. That x-axis represents a real number line that represents our quantitative variable. When we move to bivariate data, now we actually have two dimensions, and each dimension represents a variable. So we'll have the x dimension, and then we'll have that y dimension. So we're going to start with this scenario. In this scenario, we have two variables. One variable is the type of pet people have, and in our sample, people either just have a cat or a dog. And then the gender of the owner, of the person, as either male or female. So we do have two variables in this contingency table. What types of variables is presented in the contingency table? So this is an important idea because just like with the univariate case, the type of variables that you have dictate how you're going to visualize that information. It's kind of like in a univariate case, if you have qualitative data, you might look at a bar graph. If you have quantitative data, you might look at a histogram. So it works the same way when you have bivariate data. You really have to think about the types of variables that you have. Of course, there's more possibilities when you have two variables because you could have both qualitative variables, you could have one of each, or you could have two quantitative variables. So you have really three different scenarios that you can end up with. So in this case, the type, of course, pet is non-numerical, gender is non-numerical. Those both are give you non-numerical outcomes. So both gender and pet are qualitative in this case. When you have two qualitative variables, or honestly, anytime you have a qualitative variable, same thing in a single case, you can't perform any mathematical operations on the outcomes themselves because they're not numerical. So when you are in the scenario where you have two qualitative variables or a qualitative variable, you're kind of limited in terms of what you can do. Because with a qualitative variable, you can't perform mathematical operations on the outcome. So instead, we tend to look at frequencies or percentages within these categories. So we do the same thing with bivariate data. If we have two qualitative variables, essentially what we can do is we can look at frequencies or percentages within these different categories. So a good way to do that, and probably the most common way to look at two qualitative variables, is with this idea of a contingency table. So do notice we have two dimensions here. The rows represent one dimension, which in our case is the gender. The columns represent the other variable, which in this case is the pet. So one dimension is the rows, one dimension is the columns, and that's what we do whenever we move to bivariate data. We have basically an x and a y. Each represents one of our variables. So there's multiple ways to look at a contingency table. There are actually four different ways. This is the first one, which is just simply based on frequencies. This is the most common way to identify a contingency table, is just to have the frequency for each outcome in the cells. So for example, in that first cell, you see that value of 42. So that means in this sample, there's 100 people in our sample. You can see that in the bottom right corner. That is where the grand total, we typically call that the grand total of people in our sample is. Of those people, 42 are in that first cell, and that first cell is the overlap of dog owners and people who identify as male. So because of that, we have 42 people who are dog owners and are male in this sample. And that's how we interpret that information. It's really that simple. So the nice thing about this is it does allow you to look at the relationship between these two variables. because they are broken down for each combination of categories for our two variables. There are three other ways to look at contingency tables. So all these are based on percents, and as I already mentioned, we're kind of limited to either frequencies or percentages. So when you move from a single variable to two variables, there's actually more than one way to look at the percentages, because now we have two dimensions along with a grand total. So we have the row dimension, so we can base our percents based on the row. We have the column dimension, we can base our percents based on the column. And then we also have that grand total, and we can base our percents on that grand total. So here's an example where it's based on row percent, and you can see they're under cell format. In this case, the cell format tells what's included in each cell. So you can see first it gives the count or the frequency. Those are the same numbers as you saw in the previous table. In the percent, or in the parentheses, the percent is given as row percent. So even without that cell format, we can tell how the percents are calculated. All you have to do in the table is just look at where the percentages are. So you can see that the percentages in this case are in that row total column, in that last column. Those are the row totals. And since that's where the 100% are, that lets us know that these percentages are based on the row total. So the way that first percentage is calculated, that 80.77%, is you just take that value of 42 and you divide by its row total. So you take 42 divided by its row total of 52, that will give you 80.77%. And that's how each of these percentages are calculated. You take the value in the cell, divide by the corresponding row total. The interpretation of these percentages depends on how they're calculated. So it's very important that you're able to interpret it. So if you look at this 80.77%, how do we interpret that? Well, you got to keep in mind what it's based on. It's based on the row percent, which means we are limiting ourselves to just that first row. So we are only limiting ourselves to males here. So because of that, whenever we interpret it, we want to say something like this: 80.77% of males, because we're only talking about that row, are a dog owner. So for this sample, 80.77% of males are a dog owner. That's how we interpret that value. So it's very important that you pay attention to how the percent is calculated, because that's going to tell you how to interpret the value. If we switch this and base these on column totals work in a very similar way. It's just now we're going the other direction. Now, instead of the percents being in that row total column, now if you look at the bottom row where the column totals are, you will see that's where your 100% are. So the way to figure out how these percents are calculated is to always look at where those 100% are. That'll tell you. So in this case, they're based on column totals. So to calculate the percent in that first cell, we just simply take the value in that first cell, 42. We look at the column total, which is 51. 42 divided by 51, that'll give us 82.35%. So notice now in this case, we're limiting ourselves to a column, which means for that first value, we're limiting ourselves to just dog owners. So your interpretation here would be something like, for this sample, 82.35% of dog owners are male. Something like that. But when you do your interpretation, once again, make sure you limit yourself to whatever you're talking about, which in this case is dog owners. So 82.35% of dog owners are male. The last scenario, and honestly the most common scenario, is whenever we have the percents based on the grand total. And the grand total means that there's a total of 100 people in the sample, as you can see. If you look at the percentages here, the only place you see 100% is in that grand total cell. And that tells you that these percents are based on the grand total. So in this case, the calculations are easy because the grand total is 100. So when you divide something by 100, it just basically becomes a percent. So you can see in that first cell, you get 42 divided by 100. Everything's divided by 100 here. 42 divided by 100 gives you that 42% value. The nice thing about this scenario is if you add these up across the rows or the columns, these all add up. That's not the case with the other percents. With the row percents, it only adds up across the rows. With the column percents, it only adds up down the columns. it's not going to be accurate to add the other direction, because there you're basically just looking at either rows or columns, so you're narrowing it down to a single dimension. Here you're looking at both dimensions at the same time. This is the more common way to identify percents, but it depends on what you're interested in, which way you would want to calculate your percentages. So here, though, everything is just divided by 100. Everything adds up nice and neatly. This is the most common way to identify percents within a contingency table. So here it's a little different, because here now you're dealing with the whole sample, right? Because you're dividing by the grand total. So when you interpret this, I recommend you always say something like 42% of the sample, because that's the group you're now talking about. You're not limiting yourself to either a row or a column. So I would say something like 42% of the sample are both male and a dog owner. They have both characteristics. So that's how you interpret this. So with qualitative data, two qualitative variables, this is the most common way to display the information. We can display it either as frequencies or percentages within these contingency tables. These contingency tables do allow us to create these two dimensions where the columns represent one dimension, the rows represent the other dimension. Our next display is this idea of a box plot. So a box plot is also, of course, used for two variables. Let's talk about the types of variables presented in these box plots, and then we'll talk a little more about the graph. So you can see the y-axis here is miles per gallon. Miles per gallon is, of course, that y-axis is, of course, a real number line. So that real number line, miles per gallon, is a quantitative variable. So we have one quantitative variable here, which is that y-axis. If you look at the x-axis, you can see we have categories, different categories of engines here, 4-cylinder, 6-cylinder, 8-cylinder. Since those are just categories, that is a qualitative variable. So engine type here is qualitative, miles per gallon is quantitative. So let's talk a little bit about where the box plots come from. The box plots are really nothing more than just a picture of your 5-number summary. Is really what it is. So the box itself represents really the interquartile range. So like if we look at that 4-cylinder engine, the bottom of the box there is probably around, what, 23? The bottom of the box would represent Q1. The top of the box, which is around 30, would represent Q3. The line that goes through the box, which is probably around 26, that line that goes through the box would represent Q2. So when you look at the box itself in a box plot, you're really just looking at nothing more than the quartiles. You're looking at Q1, Q2, and Q3. We then have these lines that extend from the box. These are what we call whiskers. So the whiskers show the bottom 25% and the top 25% of our data. So you can see that bottom whisker in the 4-cylinder engine goes down to about 21. So that top whisker goes up to maybe 35. So you can see that whenever you look at the entire box plot, including the whiskers, you're looking at the low value, Q1, Q2, Q3, and the high value. That's what a box plot is. It's really nothing more than just a picture of that 5-number summary. So do notice the dimension that really matters here is your Y dimension. That is your real number line. Your X dimension is really just like in a bar graph where we have categories. So notice the width of the boxes don't mean anything. The width of the boxes, since the x-axis is just categories, we just make them all the same. We make the spacing between the boxes the same. The ordering technically doesn't matter. None of those things really matter because the x-axis is a qualitative variable. So the dimension you're really looking at here is that y dimension. And that y dimension essentially is going to allow you to identify your 5-number summary. So there are some common questions I give you with these kinds of graphs. So let me go over some of the questions that I would typically ask. We don't draw these graphs by hand. As we've talked about before, we'll let software do that for you. But what I typically will do is I'll give you a graph and then I'll ask you questions about the graph. So here's first question. Which engine type typically gives the best gas mileage? So I'm sure you could answer that without even looking at the graph, but let's talk about this in terms of the graph. So the first question that I'll commonly ask with box plots is I'll ask which category essentially has the highest level, because that's the highest level or the lowest level. That's essentially what we do with box plots mainly, is we are comparing the levels of the qualitative variable over this quantitative measure. So it allows us to say which type of engine typically gets the best and the worst gas mileage. It allows you to compare the levels of this qualitative variable over the quantitative variable. So without even looking at the graph, I'm sure you know a four-cylinder engine is going to get the best gas mileage, but let's talk about the graph itself and what you should look for. When you're comparing to see which typically has the highest or lowest, there's two main things that you want to look for. First, look at the median. Notice the median for the four-cylinder engine is higher on the y-axis than for the six-cylinder or eight-cylinder. The second thing you want to look at is just look at the box itself, the position of the box. The position of the box is higher for the four-cylinder engine than for the six or the eight. So those two things together tell you for sure that the four-cylinder engine typically gets better gas mileage. So when you're comparing typical values, the things that you look for is you look at the position of the median and you look at the position of the box. That'll give you a good comparison of which one typically. Notice when we talk about typically, we're not talking about the extremes. We're talking about generally or typically what happens. So you're not focusing on the whiskers or the extreme. Focus on the median and the box in order to determine which is typically higher or lower. The second characteristic that we measure is variability, and variability is the second thing I commonly ask you for in box plots. So here I say which engine has the least amount of variability. So with variability, we're talking about the spread of the data. So the more spread out the data is, basically the bigger the box will be, the longer the whiskers will be. So here we're looking for the least amount of variability. So we're looking at, with variability, you're looking at the size of the box, the length of the whiskers. So if you compare the sizes of the boxes here, you see that the six-cylinder engine has the smallest box. That means that's a good indicator that they have the least amount of variability. You should also look at the whiskers. The whiskers here are also relatively short as compared to the other two engines. So because of that, we can definitely say that the six-cylinder engine has less variability. So the six-cylinder engine has the least amount of variability. A third thing that I will lots of times ask is I'll ask about extreme values, and I haven't really talked about those yet. You will notice that with the eight-cylinder engine, you see that dot up there. And that dot, sometimes you'll see these as asterisks depending on what kind of software is used. But that dot, or sometimes an asterisk, will represent an extreme value. So the nice thing is the software does this for you, and it'll identify and say there's an extreme value here. It'll identify it as a dot or an asterisk, so you don't actually have to make a judgment call as to whether or not something is extreme. You just really have to be able to look at the box plot and know that a dot or an asterisk indicates an extreme value. So there is one extreme value here. It's that one point around 25 with the eight-cylinder engine. So box plots can have multiple extremes. Some box plots, you can look at them and they have no extremes. So whenever I ask this question, sometimes the answer is there are no extremes. So do make sure you keep that in mind. Not all data sets have extreme values. This one does. It just has that one single value. So I will tell you, when you have that extreme value there, I did say earlier that the whisker, that top whisker goes up to the highest value. So obviously it doesn't in the case of the eight-cylinder engine because the highest value is 25. And notice the whisker stops around 20. Well, basically the way it works is if the software identifies an extreme value, then it represents that extreme value by a dot or an asterisk. And then it creates the whisker to the next highest value in the data set, whatever that is. So there was one value of 25 in the data set, and then the next highest value in the data set was a value of about 20. So that's why the box plot looks like it does. The last thing, and this is always important, is the shape of the distribution. How do we determine the shape of the distribution based on box plots? So we're going to do the shape of the distribution for each of these. So I'm going to start with actually the easiest one, which is the six-cylinder engine, and then I will work my way to the other two. Let's first talk about in general how we determine the shape. So when most of us determine the shape of a box plot, we actually turn the boxes on their sides so that it's easier to see the dimensions in terms of whether it's right or left skewed, because we want things to go to the right and left if we're going to talk about right and left skewed. So most of us turn these box plots on their side. So it's very important. You got to make sure you turn the graph the correct way if you're going to do this. Because if you turn it the wrong way, then everything that's left skewed is going to look right skewed and vice versa. So you want to make sure that you turn the graph clockwise. And the key is this. Notice that y-axis is a real number line. So when you look at that real number line, it's increasing from 10 up to 30. So if you turn this clockwise, notice that that real number line will be increasing from 10 to 30 from left to right. You want it to look like a real number line. If you turn it the opposite way, if you turn it the wrong way, then your real number line will be going backward. So the key thing when you turn this graph is you want to make sure that you turn it in the direction so that your real number line is increasing from left to right. So like I said, let's start with the 6-cylinder engine. The nice thing about the 6-cylinder engine here is it's simple. So the two things you're looking for, you're basically looking at where the median is in terms of the box, and you're looking at the whiskers, the length of the whiskers as compared to each other. So the 6-cylinder engine is nice because notice the median is perfectly in the center. Notice that the whiskers are the same length. So essentially, if you fold that box plot in half, the left side's a mirror image of the right side. So if the box plot is symmetric, then it's simple. Your distribution is symmetric. I will not have you identify uniform or bimodal based on a box plot, but I do want you to be able to say, is it generally symmetric, is it right skewed, or is it left skewed? Do keep in mind that a symmetric distribution could also be uniform, but we are going to keep this pretty straightforward. Box plots we're only going to look at, is it symmetric, is it right skewed, or is it left skewed? So the 6-cylinder engine, symmetric. The box is symmetric. The whiskers are the same length. Definitely a symmetric distribution. Okay, let's look at the 4-cylinder. So the 4-cylinder, the median is definitely not in the center. And the whiskers are not the same length. So let's talk about the shape. So the median's actually left of center. So you got to be careful here because a common mistake, and I hate to tell you common mistakes that people make, but I feel like this one's important. Keep in mind the median is the line that goes through the box. That's also Q2. Exactly half your data is above that and exactly half your data is below that. So some people will look at that and they'll say, well, the right side or the top side of the box is bigger, so there's more data there. That is not the case. It's not that there's more data there. There's the same amount of data above the median and below the median. It's the fact that the data there is more spread out than the data to the left. So that's really what you're seeing. When you see the right side of the box being bigger, what you're really seeing is you're seeing the data to the right is more spread out. Well, if you think about a right skewed distribution, you have that long tail to the right. Well, the reason why you have that long tail to the right is because the data to the right of the distribution is more spread out. So when you look at a box plot, you're looking at which side of the box as compared to the median is bigger. That will indicate the direction of the skewness. In this case, if you turn this clockwise, the right side or the top side of the box is bigger. That means that indicates a right skewed distribution because the data to the right is more spread out, indicating we have a longer tail to the right. You can also compare the whiskers. That's the other thing that you should compare, is the whiskers in this case. The whisker to the right is longer than the whisker to the left, which also means or indicates a right skewed distribution. So everything here indicates this is a right skewed distribution, and that's what it is. This is a right skewed distribution. If we look at the 8-cylinder engine, it's almost the same as the 4-cylinder. We have that extreme to the right as well, but you can see the right side of the box is bigger, the right whisker is longer. We also have that extreme value out there to the right. So everything here also indicates a right skewed distribution. I will tell you that it is possible. Sometimes you can have a box that indicates right skewed and your whiskers can indicate left skewed. That can happen. Like you might have a box that looks like the 4-cylinder engine box, but the whisker to the left might be longer. So you have a box that indicates right skewed, you have a whiskers that indicate left skewed. That can happen. I wouldn't do that to you on an exam or anything like that, but it can happen. The thing is remember that this is only one of the ways that we can look at shape. There are multiple ways that we can look at the shape of a distribution. This is one of them. So if you're ever in that scenario where it seems like, well, what's the shape of this distribution? I can't really tell because I'm getting contradicting information. Then you should look at some of the other tools that we have in order to look at shape. For example, you can create a histogram and look at shape. You can compare the mean and median and look at shape. So remember, this is only one of the many tools that we have. Now, for class, lots of times you're going to look at one thing and you're going to say the shape is whatever you determine it to be. But in reality, you can look at multiple things to determine the shape of a distribution when you really conduct a study. The next graph is a line graph. A line graph is also, of course, used for two variables. We also call this a time plot. I'll call it a time plot a lot. Let's talk about the types of variables here, and then we'll talk a little bit about what we look for in a line graph or a time plot. So our two variables here, of course, the y-axis in our case is the value of a car. The x-axis is time. So in a line graph or a time plot, the x-axis will always be time. So essentially, a line graph or a time plot is used in these scenarios where we're basically looking at the values of a quantitative variable over time. So in a line graph, for our purposes or time plot, the x-axis will always be time. The y-axis will always be some quantitative variable. So both time and car value are quantitative. So when you're looking at a variable over time, you do have two quantitative variables, one of which is, of course, time. So when we look at these kind of graphs, essentially what we're looking at, is there a pattern for this variable over time? That's really the purpose of these graphs. You can take entire courses on time series analysis. So we're barely going to scratch the surface, but I do want to make sure that you're familiar with the four main components of a time series. So those are trend. Trend just means is the variable increasing or decreasing over time. So it would either have an increasing trend, a decreasing trend, or if it has neither, then we would say it has no trend. If it's constant over time, we would say it has no trend. The second one is a seasonal component. A seasonal component is where it fluctuates up and down and some pattern. A seasonal component occurs like if you look at any department store and you look at their sales over the course of a year. Over the course of years, you'll see a seasonal component because their highest sales are always during the holiday season. So that's what a seasonal component looks like. Every year at the same time, their sales numbers are the highest. So these high points are going to be consistently apart. Every holiday season, the sales are the highest. It could be something like your gas bill if you have a gas furnace. Your gas bill is always high in the winter, low in the summer. So it has this seasonal component where the high values are consistently apart, the low values are consistently apart. So that's really what you look for in a graph for a seasonal component, is you look at the high values and see, are these consistently apart? Is there a pattern to how these are occurring? And then you do the same thing for the low values. Is there a pattern to how these are occurring? If either one has a pattern, then that's a good indication that there's a seasonal component. The third one is irregular cycles. Irregular cycles are something that we can account for why it happens, but it's not something that's going to continue in some kind of pattern. It can be something like, if you look at unemployment rates in the late 1960s, early 1970s, you'll see that unemployment rates were really, really low. A big part of that is because of the Vietnam War. And during the Vietnam War, obviously that's a reasonable reason for why unemployment rates would be low, but it's not something that's going to repeat in any kind of pattern. That's the idea of an irregular cycle. It's I know I have this low point, I can account for why this low point occurred, but it's not something that's going to repeat in any kind of pattern. We don't really deal with those in this course because we're not going to really investigate the variables at that level. So we are going to focus really on the first two, which is trend and seasonal component. There is a fourth one just called random fluctuation. Pretty much all graphs have random fluctuation. It's anything that you cannot account for by the other three components. Random fluctuation is the fact that if you look at a graph, it's not going to be perfect. There's going to be some fluctuation you can't account for. I'm not worried about you saying random fluctuation every time. You don't need to say random fluctuation. I really want you to focus on the points of is there a trend and is there a seasonal component. You can always throw random fluctuation in there, but please don't make that your focus. Okay, so let's talk about the time series components in this graph. So I recommend that you always start with the idea of a seasonal component. See if there's fluctuation up and down and see if there's a pattern with high points or low points. So in this case, there really is not a big fluctuation up and down. It's pretty much just decreasing over time. So in this case, there is no seasonal component. So a seasonal component is always a good place to start, but in a graph like this, you can just look at it. There is no seasonal component. There is an overall trend. Of course, the trend is decreasing. Over time, the value of a car is decreasing, which is what you would expect. Of course, you can also say there's random fluctuation. Notice this isn't a perfectly smooth decreasing pattern. There is some fluctuation within this decreasing pattern. That's the idea of random fluctuation. Random fluctuation is included in all graphs. Like I said, you don't have to say that every time. I want you to really focus on trend and seasonal components. So in this case, the main thing I'd want you to say is that I want you to say there's a decreasing trend. Here we're looking at the product sales, or the sales for a product over the months of the year. This is over a 3-year period of time. Again, let's start with the idea of a seasonal component. So if you look at the low points and the high points, that's what you look at for seasonal component. You can see this definitely fluctuates. It starts a little bit by decreasing, then it increases, decreases, increases. So there's a fluctuation here. Notice if you look at the high points, the high points are consistently apart. And because of that, you can see that the high points tend to be around month 12, around month 24, and around month 36, if you look at the scale down there. So those are consistently apart. So there's definitely a pattern to those high points, which tells us there's a seasonal component. You can also look at the low points. You look at the low points, and you can also see that those are consistently apart. So there's definitely a seasonal component here. There's a pattern to how this variable is fluctuating over time. Let's think about trend. Trend is this increasing or decreasing over time? So when you have a seasonal component in a graph and you're looking at trend, what I recommend you do is I recommend you look at the pattern of the high points and the pattern of the low points. So if you look at the pattern of the high points, you can see those are increasing. If you look at the pattern of the low points, those are also increasing. So within this has a seasonal component, but it also has an increasing trend. Within this increasing trend, there's definitely a strong seasonal component. And the seasonal component is actually the biggest component in this case, but we also have this increasing trend over time. Like I said, a good way to look at that within a case where you have a seasonal component is look at the high points and look at the pattern, look at the low points and look at the pattern, and if you look at both of those, you'll be able to tell whether or not you have that increasing or decreasing trend. You can also identify random fluctuation, but as I mentioned before, I really want you to focus on those first two components. So that is the idea of a time series. So here's our last graph. This last graph is called a scatter plot. A scatter plot is, well, let's first just say there are two variables here, and let's talk about what they are. So in this case, we have a scatter plot that's for exam score and hours spent studying. So you can see hours spent studying is our x-axis, exam score is our y-axis. You can see in this case, both of these are real number lines. So if we think about the types of variables here, both hours studying and exam scores, these are two quantitative variables. So typically when we're looking at two quantitative variables, this is what we look at. We look at these in terms of a scatter plot. So a scatter plot is kind of like what you do in an algebra class where you plot points. But the thing you do in algebra that we don't do in here, at least not in this context where we're graphing the relationship between two variables, is we don't have like a perfect function that represents the outcomes. It's not like we're plotting points and then connecting the dots. That's not what we're doing. We're basically just plotting the points. And then we're looking to see if there's a pattern within those points. So whenever we look to see if there's a pattern within those points, we're essentially looking to see if these variables are related or what we call correlated. So we will say, is there a correlation within this graph or between these two variables? Are these two variables correlated? So the way you determine that is you basically look at the points and you determine, is there a pattern? If there's a pattern, then that means they're correlated. That's essentially all correlation is. Is there a pattern or relationship between these two variables? So this is the most common way. This is what we typically look at when we look at two quantitative variables. In the next section of Unit 2, we will actually continue to talk about this idea of correlation because we'll start to talk about how we measure it. But now we're just going to look at it graphically. So if you look at this graph, is there a pattern? Of course, the answer to that is yes. So since there is a pattern, that means there is a correlation. So with correlation, let's talk about what we're going to focus on for this course. So there's all different kinds of correlation. Correlation can really come in any form, any kind of function that you can think of, you can model data with. I'm not going to go back and make you memorize again every function that you've ever dealt with in your mathematical life. So we do in this course focus on the idea of a linear relationship. So we're going to identify correlation as either linear or nonlinear. That's where you start. Is it linear or is it nonlinear, or is there no correlation? If there's no pattern, then there is no correlation. So the first place you start is you say, is there a correlation? There is. That means there's a pattern. So if there is a correlation, is it linear or nonlinear? If it's not linear, then we will just stop there and we will just say it's a nonlinear correlation. Do make sure you say nonlinear correlation, which implies there is a correlation of a nonlinear type. Don't just say no linear correlation, because that doesn't necessarily imply that there is a correlation. So make sure you're careful about your wording there. Make sure you say there's a nonlinear correlation. So nonlinear correlation means there is a correlation of some nonlinear type. So there's a pattern that's not linear. That's the general idea of nonlinear correlation, and everything that's not linear, we're just going to throw into that one category of nonlinear correlation. Like I said, you don't have to go back and remember all the different relationships or all the different kinds of functions and patterns that you can end up with on a graph. If it is linear, then there's a few other steps, a few other things that we need to identify. We need to identify if the relationship is positive or negative. If the relationship is positive, that means the line that followed the points would have a positive slope. If it's negative, it means it would have a negative slope. We also need to determine whether or not the relationship is perfect. Now, in reality, when you collect data, you're never going to get a perfect correlation. So do keep that in mind. Your relationship is never really going to be perfect. But it's a good reference point statistically. So it's important you know what a perfect correlation is. So the only way to have a perfect correlation is if all the points are perfectly on a function. So in a linear case, like if you had perfect positive linear correlation, perfect positive linear would mean all the points are exactly on a line with the positive slope. Now when you collect data, you're always going to have variability across individuals, so you're never really going to get all the points exactly on a line. But that's the idea. That's the strongest relationship you could ever have. You have this perfect relationship where we can perfectly predict y based on x. Now, that never happens in reality when you collect data, but that is the perfect scenario. So we call that perfect correlation. So you can have perfect positive linear correlation and perfect negative linear correlation. Perfect means all the points are exactly on a line. So in this case, notice if we look at the pattern, is it linear? So of course, all the points aren't going to be perfectly on a line. There is no perfect relationship here. This is not a perfect relationship. But if we draw a line through these points, you'll see that if you draw a line through there, if you think about an imaginary line going through the middle of those points, you'll notice that all those points follow that line really, really well. So this is a linear pattern. It's not perfect, but it's definitely a linear pattern. If you draw a line through these points, you'll also notice that that line has a positive slope. So that means in this case, if you think about the correlation, you would want to identify that correlation as positive linear correlation. And that's what we're looking at with these scatter plots. We're looking at, is the relationship linear or not? If it is linear, Does it have a positive or negative linear correlation? And then, of course, always think about if it's perfect or not, which usually it won't be, but it is a good reference point, as I mentioned before. And we'll talk more about how we measure this in the next section of notes. Let's look at another graph. Are these two variables correlated? Is there a pattern in the graph? And of course, you can see a pattern there. So there's definitely a pattern or a correlation. So let's think about the type here. So this is one of those where I would actually take two different answers. If you fit a line through these points, it actually fits it pretty well. And honestly, at the end of the day, if you were going to fit this data, you would most likely fit a line to these points, because a line is going to fit them really well. And a line is simpler to interpret than a more complicated function. And lots of times in statistics, you're presenting information to people who are not statisticians. And because of that, lots of times we like to keep the models simple if it's possible to keep them simple. So in this case, it's likely that we would use a linear pattern. Now, you can also see a little bit of a curve. This is not a perfect linear pattern, because you'll notice from left to right, it starts to decrease at a relatively steep slope, but then it starts to flatten out more and more as you go to the right. So this is not a perfect linear pattern. So I would also accept here that this is a nonlinear correlation. I would go with, because ultimately, if you're a statistician at the end of the day, what you would probably do in this case is you would probably fit a linear model. I don't expect you to know that necessarily. So if you see this as a pretty close to a line, that's great, and you can identify it as negative linear correlation. I would also accept nonlinear correlation here, because it does the slope does change as you move from left to right. If you were to fit this perfectly through the middle of those points, the slope starts out steeper, and then it flattens out as you move further to the right. So with these scatter plots, that's what's important in this section, that you're able to identify the relationship or the correlation between these two variables, whether or not there is a correlation, whether or not it's linear, and then if it is linear, if it's positive or negative, and then of course you need to be able to identify if it's perfect or not. It's also important to know what the strength of a relationship is. When we talk about the strength of a relationship within a scatter plot, like if you fit a line to a set of points and the points are really close to the line, then we say it's a strong relationship. So when we talk about how strong a relationship is, we're talking about how close the points are to the line. So if the points are really close to the line, then we say the relationship is strong. If the points are not close to the line, then it may not be a strong relationship. But when you'll see that sometimes us talking about, and you'll see it more in the next section, us talking about the strength of a relationship. The strength is simply how close are the points to the line. The closer the points are to the line, the stronger the relationship is. The strongest relationship you can ever have is when all the points are exactly on a line and you have that perfect relationship. That perfect relationship is the strongest relationship you can have between two variables. And I think that's it. So the big things in this section is the four different types of displays: the contingency table, the box plots, the time plot, and then the scatter plot. These are all used for bivariate data based on the types of variables that you have. That is the end of section 2C.